in this video, we're going to look at how to rewrite statements using quantifiers, and then also convert universal conditional statement into its symbolic form. And we will also look at some equivalent forms of universal and existential statements. And at the end, we'll practice on how to on identifying universal and existential statements. All right, let's begin with the first example. First of all, I would encourage everyone to read the book examples. Those are good examples. Please note that there are different correct ways to translate from formal to informal language, which is actually a pretty easy job. And then from informal language to formal language, this is a little harder and it will take a little getting used to. However, through the practice, you'll get better and better. This is pretty important because that's how you write a less precise statement into very precise statements, which is pretty needed skill when you prove statement, when you correctly under what statement is saying. All right, the first example is let's rewrite the following using quantifiers. For all exists. Now let's read the first one. All triangles have 3 sides. So I hope that this word all kind of signals, gives us a strong signal that it is a universal statement. So I'm going to define, say, let's define, say, let T be a set that contains all triangles. And then this statement is saying, again, when we say see now, that's a good place to introduce variable, right? So that's what I'm gonna call X, a triangle. So I'll say for all X in this set T, okay, and X has 3 sides. X has 3 sides. That's how I would convert this informal statement into a formal universal statement. And sometimes if there's no misunderstanding here, we define T as triangles. If we have some context, knowing we are referring X as triangles, sometimes this can be omitted. If there's no misunderstanding, of course, here I feel like it's very necessary. Now let's take a look at the second one. Let's say no dogs have wings. No dogs have wings. That's the same as saying dogs do not have wings, right? All dogs do not have wings. So therefore, it sounds like there's a for all dogs do not have wings. So therefore, this is a universal statement. Let's define D as all dogs. And say, suppose now again, we are going to introduce variable. This basically is saying all dogs do not have wings, don't have wings. So the dog right there, that's noun. Now I'm going to introduce a variable. We do not have to stick with X. We could use any other letter that you want. I'm gonna just, for convenience, because it's dog, so I'm gonna use D to represent the dog. So I'm gonna say for all dog in this set D, all dogs, right? D does not have wings, right? The next one, some programs are structured. It says some programs are structured. It doesn't say all programs are structured. So therefore, this is an existential statement. So I'm gonna let P be, say, all programs. And then let me use lower p to represent a program. So in this case, I would say there exists a small p in the set P, which is the set of all programs, such that, so keep in mind, there is a symbol such that for existential statements, such that P is structured. Right, this is the first example, how to translate informal language into formal language. The second one is universal conditional statement. What is a universal conditional statement? It says universal, therefore you must have the exists, right? I mean, for all, I'm sorry. And conditional statement means if, then. So therefore, universal conditional statement looks like this form. For all x, if P of x, then Q of x. And the book says familiarity with statements of this form is very essential if you are to learn to speak mathematics. So we'll practice on how to convert that into this form. So let's rewrite the following statement into this universal conditional statement. And by the way, there are more than one way to translate. Different people may choose different words, but they should be the same structure. Let's take a look at the first one. If a real number is an integer, then it is a rational number. So first of all, we have to introduce for all there, okay? So in this case, I'll say for all, by the way, a real number, we have to, a real number, that means the number is a real number, right? So in other words, let's say x is a number, and this number is a real number. So I'm going to say for all x, where x is in R. Now, let's try to finish this statement by rewriting it into if-then form. And so if, so this is the if form. Well, the real number is already, this information is already represented right there in the for all part. So we don't have to repeat it. So therefore, I'm going to just say if x is an integer, if x is an integer, so x is in z, we are trying to write that using the mathematical symbol at all, if at all possible. If x is in z, then it is a rational number, right? A means the same x. Then x is a rational number. That means x is in Q. If you remember, Q means the rational number. So that's how we write this informal language into a very formal mathematical statement. Now, sometimes when there's no misunderstanding, seems like because we are talking about x in, it's pretty clear that x is a number, right? So sometimes if there's no misunderstanding, sometimes this can be omitted, like if for x in R. But I'm gonna just put it there. Let's take a look at the second one. All bytes have 8 bits. In other words, if it is a byte, then it has to have 8 bits, right? So therefore, I'm gonna say for all x, if x is a byte, then x. I don't want to use it because we already introduced the x. X has 8 bits, right? And similarly, let's take a look at the last one. No fire trucks are green. So first of all, let's try to interpret this into a statement that's easier to translate. So no fire trucks are green. We have seen like statement that involves all, right? Let's say that if we can try to rewrite it using the all, no fire trucks are green. That means all fire trucks are not green. All right, this will be a little easier because there's an all. That means we are going to say for all, okay? For all X, if X is a fire truck, then X cannot be green. X is not green. All right, so again, I try to emphasize that some people may have different way to say it. As long as we are looking at this structure, the universal conditional structure, that's the goal. All right, the next, let's take a look at equivalent forms of universal and existential statements. The first one, for all X in U, U is a universal set. So oftentimes, if there's there's no misunderstanding, sometimes you just simply skip that. For all X in U, if P of X, then Q of X. And for all X in D, where Q of X. Now, oftentimes, we can rewrite this into this equivalent form, where this D is the truth set of P of X in U. Basically, what it's saying is we actually can combine these two to make this universal conditional statement into a universal statement. There's no if-then structure anymore. Now, this is pretty important because if you are able to do that, you are likely to be able to do the backwards. So oftentimes, in the future, when we prove statements, it's pretty important for you to be able to translate this, you rewrite a universal statement into a universal conditional statement so that you know what's given, what's to be proved. So this is an important skill. Let's practice this way. Rewrite this form into this form, okay? The trick is to combine these two together, the properties together. For all students X, so what is X? X is just a student. If X is a CSC major, then X has a favorite subject. Now, let's try to rewrite this into universal statement only. And do you see that the second part should be the same? X has a favorite subject. The trick is to combine these two, okay, these two. So we are gonna just say for all CSC major students X, okay? So for all CSC major students X, X has a favorite subject. Simply combine these two. Now, similarly, we have look at the next statement. There exists X in U, the universal set, such that PX and QX. So very similarly, we can actually combine these two. We can combine these two into a existential statement. Let's take a look at this example. There exists an MCC student X such that X is a CSC student and X is skinny. All right, so the goal is to try to combine these properties into one. So I'm gonna say there exists MCC CSC major student X such that X is skinny. Now, sometimes be aware that we sometimes have this so-called implicit quantification. So be aware that the quantifiers may not be explicit in some statements. So you sometimes have to use your life experience to identify whether it is actually a for all case or the exist case. So is that a universal statement or existential statement? Of course, the more you do it, the better you will be. Let's take a look at this one. If a student is an MCC student, then he or she has access to Omaha libraries. So if you read this, you can actually feel that as long as a student is an MCC student, right? In other words, all MCC students, they have access to Omaha libraries. So this actually means all MCC students. So which is, this all means this is universal statement. Now take a look at the second one. X cubed plus 1 is equal to x plus 1 times x squared minus x plus 1. This actually is an identity. That means this formula is actually true no matter what x value you have. So it is true for all x. So for all x, that means it's a universal statement. Now look at the last one. This last one, when you solve an equation like that, obviously some 0 cannot work, right? 0 plus 1 is not equal to 9. However, if you say 2 cubed plus 1, like 0 cubed plus 1, that means 0 plus 1. So now if you try x being 2, so 2 cubed plus 1, is that equal to 9? Of course, it is equal to 9. In other words, this statement, sometimes it's true, sometimes it's not true. By the way, this is, sometimes we call it open sentence, open statements, because it is true sometimes, it is true, false sometimes. So this one certainly will not be universal because it's not true sometimes. But you are able to find some value. So there exists some value, at least one value, so that this is true. We can see that this actually is existential. And you can see that there's no words telling us directly whether it is universal or existential. So in this case, it is a little implicit. We're going to close this section by introducing this notation. Px implies Qx means every element in the truth set of P of x is also the truth set of Q of x. And this, when you have double arrow here, that means they both have the same truth set. If x makes P true, then x Q true, vice versa.